Good afternoon. It is 1 o'clock, so I will go ahead and get started. I know some more people will be joining in as we go along. I am going to be recording this presentation and we'll post it on the IGWS Facebook page and a couple other places after the event is over as well. My name is Sturgeon, and I am the outreach coordinator for the Indiana Geological and Water Survey. I'm really thankful that you all have come in to join me this afternoon. I'm going to be covering kind of a basic overview of Indiana geology. We're going to cover roughly 450 million years of geologic time in about an hour. So it's going to be kind of a quick overview, but if you have any questions throughout the entire presentation, you can go ahead and put them in the chat, and I will answer them either at the end of the program, but I'll also make sure to type up the answers into the chat as well. And those comments will also be posted on our Facebook page. Okay, the presentation will be a mixture of back and forth between me talking directly into the camera and also sharing my screen so that I can show you maps and different diagrams. When we're talking about the geology of Indiana, I typically split it into looking at the bedrock geology, the superficial geology, and then sort of the combination of those things to look at physiographic regions. So I'm going to go through each of those things today. All right, let me go ahead and pull up to share the screen. And we will get started. Okay, I like to call this basic overview oceans, uplifts, and ice. Indiana has had several different environments over the past 450, 500 million years. When we're looking at geology, we're always comparing the past to what we see today in the present. So we look at environments that we have on Earth today and that helps us understand the environments that once existed throughout geologic time. Of course, the Geological Survey, who we are a state organization that was established in 1837. There's David Dale Owen, our first state geologist. We were founded down in New Harmony, and then we moved up to Indianapolis, and we've been on the campus of Indiana University since 1919. But our mission is to provide geologic information that contribute to the state's health, safety, and welfare. Here's a little bit of what I'm going to be going over today. So we're going to talk about the study of Indiana geology, just what is it and how do we do it. Again, breaking down the geology into what's on the surface and then what's below the surface with the bedrock. We'll look at the major structures that are shaping that bedrock, the combination of things in the physiographic regions, and then we'll take a little trip through time to see where Indiana has been and how it has looked throughout geologic time. So first of all, the basics. What is geology? Geology, of course, is the study of the earth. The word itself comes from the Greek words geo and logos, earth and study. And really the key when we're looking at geology is this principle of uniformitarianism, which is the present is the key to the past. When we're looking at modern day environments of deposition and modern day habitats, that helps us to understand what has happened throughout geologic time. So to study how Indiana has changed throughout time, we do a variety of different techniques. Geologists, we rely a lot on field work, so actually putting boots on and going out into the field and collecting specimens and making observations. You can see two of our geologists on this bottom right-hand picture are collecting some specimens of some glacial sediment out in the field that's in central Indiana. Remote sensing is good for areas where we can't actually get at the sediment or the rock itself. Much of Indiana, as we will discuss, is covered by a thick layer of glacial sediment. And so we can't actually see bedrock for a good portion of the state. So we have to use other methods to tell what's down there. So that's something called remote sensing. In this top right-hand picture, we have one of our geologists pushing a ground penetrating radar cart. So it's sort of like the sonar that they send off of big naval boats. It pings down a radar beam and it bounces off of different layers of rock. And it doesn't tell us what the rock is, but it tells us the orientation of those layers of rock. and the different densities of them. So it can give us a good picture of what's below the ground. And then to go a step farther, we go to this third bullet point, core drilling, where we drill for geologic core. There's a picture of a box of geologic core here in the bottom left-hand portion of the screen. The core is sampled, and most of them are about 2 inches in diameter. Some of them get up to about 4 inches in diameter. And then the picture here, the circular sample has been cut in half. So the flat side is this portion that's been cut. Core is where we pull up a sample of rock sediment, sometimes groundwater, other things, so that we can see what's below our feet. Every place on this map with a red dot is a place where we have drilled a well and sampled, particularly for petroleum, oil, and gas, which is why you see so many dense numbers of dots here in central eastern Indiana and down in southwestern Indiana. Those are 2 areas where we have oil and gas fields. But you can see it's a pretty wide coverage. And we keep this core in a core library so that our geologists and other researchers from around the world can come and access it for research and education. Much like a public book library, you can come and check out the core, do what you need to do with it, and then you return it to us so we keep it in perpetuity for research sake. If we combine all of these sources of information, we can put that data into a computer and do different methods of modeling. We can also get specific ages of the rocks and sediment and the minerals that they contain through different radiometric dating techniques. So these are just a variety of ways that we study the Earth here in Indiana. Okay, if we zoom out at the whole big picture, this is a geologic map of the United States where all of the different colors are different ages of rocks. And you can see it's a really beautiful map, and there's some kind of large scale patterns that we see when we zoom out to this scale. Out east, for example, all of these thin, skinny lines squished up against each other, those are the Appalachian Mountains. So we have different ages of rock that have been stacked up and squished close to each other when the mountains were forming. If we look at the state of Michigan up here, looks like a mitten, you can see there's sort of a circular pattern. So that tells us that the different ages, there's some sort of age in the middle, and then another age that surrounds it, and then this other age that surrounds that. If we go out west, it's much more complicated west of the Rocky Mountains because they have much more recent geologic events that have formed their surficial geology, a lot of volcanic activity and tectonic activity. So just sort of looking at this broad scale, you can see that the United States has a very complex tapestry of geology, but we want to zoom in a little bit closer and look specifically at Indiana. When we do that, again, we split geology into the study of what's at the surface and what's below the surface, the bedrock. And I'm going to be talking about both of those. I'll start with what's on the top. So surficial geology, you can see looking at this map, each different color on this map is a different kind of surficial sediment or material. And then on the bedrock map, each color is a different age of rock. And I'll talk about each of these individually. So let's start at the top and work our way down. Surficial geology is the study of unconsolidated deposits. So this is sediment that isn't hardened into a rock. It has not been lithified. It's loose, unconsolidated material that's sitting on top of the surface. In Indiana, it's all a maximum age of about 2.6 million years or younger, and it covers roughly 2/3 of the state. So when I mentioned that we have to rely on remote sensing and geologic drilling for much of the state, that's because most of our state's bedrock is covered with this thick layer of unconsolidated sediment. It gets anywhere from 0 feet in thickness down here where this red line is, all the way up to about 450 feet thick up in the northeastern part of the state. So what that means is if you're standing up here in Steuben County, you would have to drill down through 450 feet of sediment before you even hit bedrock. So very, very thick up there. That's because that's the last place that the glaciers left the state of Indiana. Okay, and I kind of gave it away a little bit, but let's keep going. If we look at the different kinds of sediment that unconsolidated sediment includes, we have 4 main types, and those are the 4 main types that are shown on this map. In the top left-hand picture here with the shovel, that's sediment called outwash. It's a mixture of sand and gravel, and you can see that the sand and gravel layers have stratified themselves by size. There's a layer of sand and then a layer of these pebbles, this gravel layer, and then another layer of sand, and then another layer of gravel. So there is some sort of sizing difference to the material. It's been sorted in some way. Outwash is deposited by fluvial activity, so moving water in streams, for example. And this broad green area in the central part of the map is a lot of different outwash deposits that have been deposited in the past 2.6 million years. Kind of the opposite of that would be this top right-hand photograph, which is the sediment called till, T-I-L-L. It is, unlike outwash, it is a mixture of every different sediment type. It can be everything from silt and very, very microscopic grains all the way up to giant boulders and cobbles. So it's a mixture of different sediment grains. There's no sorting to the grain size at all. You can see there's a big cobble here and then a lot of fine-grained material as well. So till is also covering a lot of this middle part of the state. This is actually called the Central Till Plains. Okay. In the bottom left-hand side, this dark gray colored material with the trowel pointing into the picture, that is called lacustrine sediment or lake sediment. It's basically fine-grained mud, fine-grained silt sediment. Imagine stepping into the bottom of a lake, you get that muck in between your toes. Lacustrine sediment was deposited in glacial lakes. And then we have the bottom right-hand photograph, this sort of orange tan colored sediment is loess, L-O-E-S-S, loess. It is wind-blown dust. So you take sand and gravel, for example, the wind picks it up, blows it very far. The farther you transport a sediment, the more it breaks down. So this has been transported a pretty good distance and is broken down into very, very small grain-sized particles. Loess we find along the western banks of a lot of our rivers, particularly the Wabash River over here in western Indiana. Okay, and I kind of mentioned it a few times, but when we talk about unconsolidated sediment, it has all been deposited in the past 2.6 million years by glaciers. The most recent ice age began about 2.6 million years ago with the Pleistocene epoch. And so large sheets of ice have come and gone throughout the state for several million years. And when we think about ice sheets, I mean, we could have a whole presentation just about the ice age itself, but you don't want to think about one solid sheet of ice. These were interlapping lobes of ice that were always competing for space, and they were descending into Indiana, and then it would warm up a little bit and they would retreat a little bit, and then it would get colder and they would go back. And so they were overlapping each other and always coming and going. So that's why we have this really complex map, because as the glaciers were moving sediment along, either eroding it or depositing it, when the glaciers started to melt, they would leave behind sediment that then would get overlapped or eroded by the next glacier. So a really complex history, which is why we have geologists who spend their entire careers just understanding the Ice Age geology just within the past 2.5 million years. Glaciers largely left Indiana about 12,000 years ago. They left up here in the northeastern part of the state into Ohio and Michigan, and then later retreated up into Canada. Okay. If we take all of that glacial material and we scrape it all off, okay, mentally, or we just dig down below it, we get to the bedrock, the hard rock that's underneath all of these unconsolidated deposits. And the study of that hard rock is known as bedrock geology. In Indiana, all of our bedrock is about roughly 500 to 250 million years old. MYA stands for million years ago. So at its youngest, our rocks are 250 million years old, and they were deposited in a variety of environments, unlike the unconsolidated sediments, which all came mostly from an ice age environment. Our rocks have been deposited when we were covered by an ocean, when we were covered by rivers in a fluvial environment or sort of a swampy forest environment. And I'll talk about each of these. The 6 most common rock types in Indiana, because of those depositional environments, are sandstone, limestone, and dolostone. And then this black, thin, platy rock is known as shale. Conglomerate, which is just a conglomeration of a bunch of pebbles, quartz pebbles put together, and then coal, the rock that burns. Of course, we do have other rock types, but these 6 are the most frequently ones found in Indiana. Okay, notice that they're all sedimentary rocks. We do not have metamorphic or igneous rocks within our superficial bedrock. Okay. When we're looking at the map here, again, this map shows different colors represent different ages. You can see that there's sort of a pattern. This lightest pink down by Cincinnati is sort of surrounded by this pinkish purple color. Okay, so the pinkish purple kind of loops around the lighter pink. And then the blues also loop around the purple. And if we were to extend into Illinois, you could see the blues do the same. And then if we were to also extend into Illinois and Michigan, we would see this green color go up and around and over into Michigan. So there's sort of this kind of semicircular pattern surrounding the Cincinnati area. And there's a reason for that. And the reason is the geologic structures that shape our bedrock. When we talk about geologic structures, we're talking about 4 main things. So these are the structures that are arranging our bedrock. We have 2 big basins in Indiana. Okay, a basin being some sort of depressional area. The Illinois basin takes up much of the southern part of the state, and it extends, of course, into Illinois as well as western Kentucky. The Michigan basin, aptly named because it's all of Michigan is one giant basin, and it extends a little bit into northern Indiana. And then in between those 2, we have an arch. It's known as the Cincinnati Arch down south, and then it changes its name to the Kankakee Arch. You go up north, and then it changes its name again to the Wisconsin Arch and the Minnesota Arch. It's all the same thing. They just apparently can't agree on a name. I'm going to unshare the screen, and I'm going to show a little diagram with my hands. So let's use a prop here. If this is a depression, say the Illinois basin, and then over here is the Michigan basin. So we have the Illinois basin, the Michigan basin. In between them is that arch, the Cincinnati Arch or the Kankakee Arch, whatever you want to call it. Okay. So there's an arch separating these 2 basins. So all of the rocks on one side of the arch are dipping down towards Illinois, and the rocks on the other side of the arch are dipping towards Michigan. Okay, I'm going to come back to this, but I'm going to go back to sharing the screen first. Okay, and then there are also faults, and we'll come back to those as well. Okay, looking at that arch. The geologic name for an arch is an anticline. So you can see in an arch or an anticline setting, the oldest rocks are going to be in the middle at the bottom. This is just a principle of geology that the oldest rocks are at the bottom, and over time, the younger deposits gets laid down on top. But if we were to stop deposition and begin eroding those rocks or sediment, the oldest rocks are going to be exposed in the middle. Okay, so you can see on this diagram, we went from having the yellow at the top and then orange and then blue, and now we've eroded down to where we have yellow exposed in the middle here. The older rocks are in the middle. Okay, and the same thing, if we just change the orientation, turn it sideways, you can see that the older rocks are in the middle here, been eroded away. Okay, but this is for an anticline or an arch that's perfectly upright. Geology is pretty complex, and through a number of tectonic events, Indiana's arch has been slightly inclined or dipping, so it is actually plunging towards Chicago. I'm going to stop sharing and use my diagram again for my handy envelope tool. Okay, so again, here is the Illinois basin, here's the Michigan basin, and then the arch in the middle. So in the beginning, I talked about that the arch was just standing upright, but it's actually dipping towards Chicago. So going to pretend that you all are Chicago and the arch is dipping towards you. And so you can see that the rocks have now been tilted up. And up here is roughly the Cincinnati area. This is now what's at the top here exposed in the middle. And the Cincinnatian rocks are the oldest rocks in the state. So the oldest rocks are exposed in the middle, kind of sticking up, and then everything around it is getting younger and younger. I'm going to go back to the screen and show that on the geologic map that we saw before. Okay, here we are. So here's those oldest rocks around the Cincinnati southeastern part of the state. And then we have younger rocks here in the purple. Blue rocks are younger than that. And then the green rocks are the youngest in the state. Talking about oldest and youngest, we use geologic periods to describe those. So the oldest rocks are Ordovician in age, roughly 500 to 435 million years old. And the youngest rocks are Pennsylvanian in age, roughly 325 to 250, about 300 million years old. Okay, so on each side of this, that dipping, the tilted rocks on each side of the arch, it's about 15 to 30 feet per mile is the average dip. So if I was standing here in Bloomington and I go 1 mile to the southwest, the rocks that are at the surface where I go 1 more mile, they're now 30 feet below the surface. If I go 2 miles, they're now 60 feet below from where my original point. Another mile, they'd be 90 feet down from my original point. It sounds like maybe a big dip, but that's a very, very gradual, less than 1 degree of tilt. And so it takes all of those different points that we poked holes in the ground, we collected geologic cores, we can track that dip over long, long distances. And so that's how we've determined that rough angle of incline. All right, I'm going to go back again to talk about faults. So the Illinois and the Michigan Basin and then the arch in between is what's shaping just the general bedrock shapes of our state. And then in areas where we have these black lines, we have areas of the bedrock that have been broken and shifted due to earthquakes or tectonic activity. And those are called faults. So we'll go up here. If we take a look at this map, you can see most of the faults are down here in the southwestern part of the state. There are a few in the central and northern part of the state. They are all buried below the surface with the exception of 2. The Mount Carmel fault from Monroe to Washington County, that one's exposed at the surface. And then the Kentland disturbance is also exposed at the surface. The rest are all buried thousands of feet below the ground. In the Wabash, or the southwestern part of the state, there are so many faults that we kind of group them all together and we call it the Wabash Valley Fault System. You can see the faults run roughly diagonal north, south, east, west here, and they're grouped roughly between Evansville and Vincennes area. That's going to be the most seismically active part of the state because that's where the majority of our faults are. We have had 200 earthquakes that people could feel, meaning a magnitude 3 or higher, in the past 200 years within Indiana's borders. So 200 earthquakes within the past 200 years. That does not count earthquakes that we could feel that originated outside of the state, like Illinois, Kentucky. Of course, the seismic waves don't stop at the state boundary, but 44 earthquakes in 200 years is kind of a nice even number there to remember for earthquakes that have originated in Indiana. Overall, our position here in the central United States, we are number 3 for seismic risk in Indiana and the central US. It's usually something surprising to most people. California and Alaska are 1 and 2, and that makes sense. They're on tectonic plate boundaries. They get a lot of earthquakes. If you ask people what states do you think of with earthquakes in the US, they would probably say either California or Alaska. But the central US is sitting on 2 large fault systems, the Wabash Valley, which we talked about, and then the larger New Madrid fault system, which is further down south, running roughly along the Mississippi River near Memphis area. And it's uncertain whether those 2 fault systems are combined or if one is controlling the other. There's still more research that needs to be done. But regardless of that, the earthquakes in either fault system affect Indiana, which is one of the reasons that this whole region is number 3 for earthquake hazards. Okay. Kind of an interesting note. This is something that has not been conclusively proven through research, but we had a geologist take all of those faults and then stretch them out and kind of look at the different orientations of those faults. And you can see again, they run roughly diagonally one direction and then the other, north, south, east, west here. And kind of this person who did the research, they compared it to the orientation of our rivers, which if you compare, they do run roughly diagonally one direction and then the other, much like our faults and our joint patterns. Even the Ohio River along the southern border of the state, it goes kind of diagonal down and then it cuts up and then it goes down and it cuts up and it goes down and cuts up, just like the pattern of the fault systems. This would be something that would take a lot of research, a lot of drilling for cores and remote sensing to determine, but it's kind of an interesting observation and hopefully one that we can look into further. Okay. One more geologic structure that I like to point out. So I mentioned there were 2 faults at the surface that we could see, the Mount Carmel down south and then the Kentland disturbance. The Kentland disturbance is interesting because it's a meteor impact structure. We have that in Indiana. It's in Newton County, and you can see it's this roughly circular pattern where the rocks were impacted and have actually been broken and are now tilted almost vertical at the surface. And the oldest rocks are Ordovician in age here in the center. And then the impact cut a channel that was Pennsylvanian in age, so around 300 million years old. We don't have an exact age for this impact. We know that it was sometime after the Pennsylvanian period, but before the Ice Age, because Ice Age sediments set on top of the impact structure. So that's a pretty big relative age span, but hopefully with further research we can narrow that down to a more absolute age. Here's some pictures of it. It's pretty wild to see. You have rocks that are standing up straight. That's not something that you normally see in Indiana or most other places. So very high degrees of incline here. The rocks were literally shocked and bounced back up to be vertical. And we see lots of different evidences when we look closely at the rock, especially under the microscope, that tell us that this was a meteor impact crater and not some other kind of disturbance event. Okay. Because rocks of Ordovician age are exposed at the surface, whereas normally they would be buried hundreds of feet below the ground, a quarry company, the Rogers Company, has put a aggregate quarry on top of the impact, and they are quarrying rock that would normally be inaccessible. It would be too deep to economically quarry. So they're having an economic boon from this geologic structure, but fortunately they put a observation tower and they invite school kids to come see it, so it's kind of a nice geosite for people to visit. Okay, I'm going to pause now to see if there are any questions. If you do, just put them in the chat and I can answer them, and then I will keep going to combine all of those things. I mentioned that we have an hour for this program. It's probably not going to take the entire time. I like to leave time for questions at the end, but I want to pause and see if there are any questions now. Yeah, okay. I'm going to keep going. So when we combine the bedrock below the ground and the superficial geology on top of it, and we see what we see at the surface, that's something called physiogeography. So I'm going to share the screen back again. Okay, so this is a combination of those bedrock structures, the bedrock itself, and the unconsolidated unconsolidated sediments on top to see what the landscape actually looks like at the surface. The state can be divided into 4 main physiographic regions. So again, these are based on geographic features from that underlying geology. Okay. The 4, I'll go back here, the 4 main physiographic regions in the greens up north, that's the northern Monroe and Lake region. This kind of pink area just to the west or east of Fort Wayne, that's the Maumee Lake Plain. The blues color here is the Central Till Plain region, and then down south with the pinks and oranges is the Southern Hills and Lowlands. You can see on this map, which is available for free on our website, you can see that each of those main regions can be broken apart into sub-regions, so even more distinct, describable regions of physiographic provinces. But we're going to stick to the broad main 4 regions to just describe the overview. Okay, so starting at the north, starting at the top and working our way down again, the northern moraine and lake region is aptly named because it is characterized by natural lakes, sand dunes, and large moraine ridges. This topography up north is almost entirely created by glacial action, either the deposition of glaciers or the erosional action of glaciers. This is where up in the northern part of the state we have bedrock being covered by up to 450 feet of unconsolidated sediment. So you have sand dunes, of course, around the Lake Michigan area, but in other areas where we had standing pools of water for a long time, glacial meltwater, which of course is what ended up forming Lake Michigan and the other Great Lakes. We have moraine ridges where glaciers, the ice lobes stopped for a period of time and would start melting off all of the sediment they had accumulated, forming a large ridge. If we look particularly over in the northeastern part of the state, you can see the rivers form this kind of circular pattern along those moraine ridge boundaries. And then we have lakes up here. This is probably the most frequently common area for natural lakes in Indiana, whereas down south in the central part of the state, they are man-made lakes. But all of the lakes up here are natural. Most of them are called kettle lakes, meaning a chunk of ice broke off of the ice front and melted slowly to form a depression, which is called a kettle. So lots of those little chains of small little lakes were formed by melting ice blocks. Okay, the Maumee Lake region, which is just outside of Fort Wayne to the east of Fort Wayne, is a large flat lake plain with a few low beach ridges on the sides. This is a relic of Glacial Lake Maumee, which was a very large lake, roughly the size of modern-day Lake Erie, that was from Indiana and extended into Illinois. It was contained by a moraine ridge, and about 17,000 years ago the water overtopped that ridge and burst through, and so we had a giant flood come out of Glacial Lake Maumee, and it flooded into Indiana. And so this torrent or glacial flood that extended out of Glacial Lake Maumee is what carved the modern day Wabash River, and we'll see that in the next slide as well because it affects into the Central Till Plain. But the Maumee Lake Plain is the lake that eventually carved some of the features we see in the Till Plain section along the Wabash River. Okay, moving to the next one, the Central Till Plain region, very aptly named. It's large, big deposits of sweeping till plains. So that mixture of different grain sizes all kind of jumbled together is what we see in this area. This is mostly erosional features from the advance and retreat, the motion of glaciers throughout the Ice Age. And any place where we have bedrock exposed is where we had meltwater carve deeply down to carve these kind of entrenched valleys. Like I mentioned with Maumee Torrent, where we had that lake plain, it burst through and it carved the Wabash River here. So we have several areas where we have bedrock exposed, particularly around Peru and Wabash. Those are areas that were carved out by the the torrent there, as well as over here in the central Wabash Valley. Think the Turkey Runs and Shades area. We had glacial floods there as well, where large amounts of meltwater were able to carve down through the sediment and expose bedrock there. Okay. We also have some bedrock exposed along the Whitewater Valley River over in the Richmond area as well. Okay. Further down into the south, we have the Southern Hills and Lowlands region. This is everything from those rugged uplands that we see in the Bloomington area all the way down to kind of New Albany. There's a large upland there. We see carved in valleys and trench streams, meaning the streams have carved themselves down into a very steep V-shaped valley. The upper limit of the Hills and Lowlands region is the latest stage of glaciation. We've given a name to that called the Wisconsin stage. So this is the most recent ice age front that came down, and it stopped roughly around Martinsville and Columbus. So this kind of line here that extends, this is the furthest south that the last glacier got. Of course, earlier glaciations went as far south as the Ohio River, but the most recent glacier went as far south as Martinsville, Columbus area. And so when it started to melt, all of that water carved valleys into the Southern Hills and Lowlands. So when you think about the hills of Brown County, for example, you have this very resistant sandstone and siltstone that has been carved out by glacial meltwater coming off of the front of the ice slopes that stopped in the middle part of the state. The bedrock gets younger as you go to the southwest because of that dip into the Illinois Basin that we talked about earlier. So the arch, the Kankakee and Cincinnati arch starts right around Cincinnati area. And so all of the bedrock, the oldest is in the Cincinnati area, and it gets younger as you go over to the west. Okay, the two areas where we have caves in southern Indiana are going to be the Muscatatuck Plateau and the Mitchell Plateau. These are both areas where limestone is exposed at the surface, and then because it is dipping towards the southwest, water is able to get into that limestone, which has been jointed or fractured, and then it flows through those fractures to erode away and dissolve the limestone to form caves. So we see caves in those two areas just because limestone is at the surface and it is dipping the direction it needs to go. Okay. If we were to drill one giant drill hole and collect every single rock type that exists in Indiana, this is roughly what it would look like. That doesn't actually exist in real life. The rock layers are not continuous. They're not single layers that exist under the ground. They get big and swell, and then they pinch out. They get smaller. There are areas where there just was no deposition for certain points in time, and these are all things that geologists have to figure out through those different kind of observational techniques. But by piecing it all together, this is roughly what the stratigraphy or the layers of rock look like in Indiana. We give these rocks names so that we can communicate with other geologists about them. The oldest rock layers is the Mount Simon sandstone. So this is down almost a little over 2,000 feet below the surface. And as we get, it gets up to 2,000 feet thick. It's several thousand feet down below the surface. So this would be the oldest sedimentary rock that we have in our core library. As we go up, you can see it's a lot of limestone, a little bit of sandstone, which is represented by the yellow dotted pattern. We have shale, which is this gray pattern with the lines, and then more limestone, which is the blue bricks. Okay, also dolostone, which is where the bricks have a diagonal line. Then we have a large time period where we have shale. It's called the New Albany Shale. If you're driving south on I-65 towards Louisville, you'll see black rock on the sides of the highway. That's the New Albany Shale. Okay. Then we go up and we get a big chunk of limestone, The limestone gets particularly thick here in the Sanders group. That's the famous Indiana limestone or Salem limestone, which is used as a dimension or building stone. Okay. Then we get into this time where we have interspersed sand and limestone, sand, limestone back and forth. And then finally at the top, lots of shale, and then the black rock is coal. Okay, so how did we accumulate all of this? Why do we have large periods of just limestone, and then at other times we have sandstone and limestone interspersed? Well, that has to deal with the environment that these rocks were deposited in. Okay, so this is where we're going to take a trip through time. Beginning in the Cambrian time period, roughly 542 million years ago, we can see that Indiana was underwater. Okay, in this map here, of course, Indiana didn't exist, but we've superimposed the state outlines for the United States here. And we were south of the equator. Okay, so we were in a warm ocean south of the equator. The Cambrian time period is notable for this influx of oxygen into the oceans. For a long time, we had small amounts of oxygen building up into the atmosphere, and by the Cambrian time period, there was enough oxygen to begin to support multicellular life. So we began to see a rapid diversification of the organisms that are now preserved in the fossil record. Largely thanks to these kind of funny looking mounds. This is cyanobacteria that photosynthesizes, and so through that photosynthesis process, they release oxygen into the atmosphere. These are called stromatolites. They're still in existence. This picture is from Shark Bay, Australia. You can see them in the Bahamas and a couple other places, but a large part of that oxygenation of the atmosphere, we give credit to stromatolites for that. So during the time period, we were depositing a lot of sandstone, so you can see we were kind of in more of a beach environment, and then limestone, which is when we had a little bit deeper water. Okay, so, but we were still in that ocean-like environment. All right, moving ahead into the Ordovician time period, we were still underwater, but we are actually deeper underwater at this point. If we go back, we can see that there was a land mass in what is now North America, and it was kind of separating these two ocean basins, the one out west and then the one in where Indiana is located. If we go ahead into the Ordovician time period, that land mass has been now flooded, and those two ocean basins were now connected. That's what's called the Richmondian invasion. It's basically the first evidence of invasive species. So we had critters from the west. There's now enough water so that they can swim on over into Indiana, and they begin munching away on all of our critters. So we see a lot of different fossil species in our rock record, particularly a lot of brachiopods that we didn't see in the Cambrian period because they are now able to travel over from a different region. So this is really the beginning of seeing a lot of marine invertebrates in our rock record. This is when we begin to see corals in our rock record. And then at the end of the Ordovician time period, there is a mass global extinction due to a couple different pulses of glaciation up at the North Pole, and worldwide we see a large extinction in species. So a lot of different brachiopod species. That's probably the most common fossil type if you're looking at an Ordovician rock from Indiana. But then at the end of the Ordovician, a lot of those organisms will go extinct. You can see rock layers, a lot of limestone because we were underwater, and then deep ocean sediments forming shale. Okay. In the Silurian period, we have a shift. We are still underwater, but you can see a lot of the rest of North America, or what becomes North America, is exposed on land. And so we begin to have what are called pinnacle reefs, where there's small patches of reefs flourishing, where we have coral and brachiopods living in these kind of shallow ocean environments. And then in the deeper, more quiet water areas, we have things like trilobites, gastropods or snails, and cephalopods. The Silurian period is where we see the development of jawed fish, and so we have large predators. Throughout all of this, we have, always predator-prey relationships, and we see these preys begin to develop more complex shells to try to ward off their predators. So a lot of biodiversity that we can ascertain from the fossil record there. In terms of the rock record, it's all limestone and dolostone because we were in that ocean environment. One of my favorite places to see Silurian rock in Indiana is a place called Hanging Rock. It's near the town of Lagro along the Wabash River up in north central Indiana. And that's one of the areas that was exposed by the Maumee Lake torrent. So when the Maumee Lake flooded out, it carved away a lot of softer sediment and rock, but the dolotomized reef area here was more resistant, and so it stood out, called clintars. They're just these large standing areas of rock that are in the middle of a riverbed, and you can actually climb up to the top. There's not a whole lot of fossils still into the rock. The dolotomization process kind of destroyed some of that fossil evidence, but you can see a little bit of it, but it's just kind of a neat story, and you can get a lot of geologic history just from visiting one place. Okay, the Devonian time period, so 416 to about 359 million years ago. This is known as the age of the fishes. We are still in an ocean environment, but we have a series of patch reefs extending across the state, and then in areas in between those reefs, we have more deep water with more organic material accumulating. So geologically, that's forming limestone and then shale in the deep water. To the east of us, we have the beginning of the Appalachian Mountain Formation. This is from a tectonic collision where we have proto-continents colliding into what is now North America. It was sort of a zipper action where it started up in the northeast, and then as the continents began to collide, they began to kind of form together as we form towards the southeast. So when that tectonic activity is happening out east, you're building up land masses, and then Mother Nature, wind and water, is always going to break down those land masses through erosion. And so as the Appalachian Mountains are being formed, they're also being eroded, and those sediments are then transported west towards Indiana. So we see the sediment that is broken down from the Appalachian Mountains in our rocks beginning in the Devonian period. Okay. At the end of the Devonian period, there was a mass extinction that eliminated about 75% of all marine life. So all of these beautiful corals down at Falls of the Ohio, for example, many of them went extinct at the end of the Devonian period. Falls of the Ohio is a world-class fossil exposure site. If you have not been there, I highly recommend it. It is one of the best fossil exposures in the world, and it's sitting along the southern banks of Indiana and Kentucky. Okay. The Mississippian period, which is my personal favorite. So this is known as the Age of Crinoids. We have, again, the Appalachian Mountains are forming to the east of us, and that rock is being weathered down, and the sediments are eroded, transported to Indiana. So those big rivers that are transporting that sediment, sand and silt and gravel from the Appalachians, they're coming across into Indiana in sort of these large deltas. Think about the modern day Mississippi River Delta, which today flows down through the central part of the state and then deposits in this big, broad fan-shaped delta into the Gulf of Mexico. That fan-shaped delta would have been in Indiana as it flowed from the east, from the Appalachian Mountains. Okay, so we had large periods where we were covered by shallow oceans and what's called a carbonate shoal. This is just a shallow ocean environment where you could see the sand is moving around, much like the Bahamas today. We looked a lot like the Bahamas during the Mississippian time period, and that's when we were forming the famous Indiana limestone. Okay. Periods where we have more of the sand is when we would have an influx of sediment from the east from our rivers and deltas, and then the waters would rise again and we would become more ocean environment, and then the waters would sea level would lower and we would have more fluvial activity, and then more oceans, fluvial activity, and then oceans. So that's why we have this back and forth of sand and limestone deposits. When we go up to the top of the Mississippi, or the end of the Mississippian time period, this kind of squiggly line here, there was a large scale erosional event at the end of the Mississippian time period that eroded a lot of the different rock. So that's why you don't see the same rocks throughout all of the state. It was a large period of erosional activity, the boundary of the Mississippian and Pennsylvanian period. Okay, so here's that same erosional time, which we represent with that wavy line. Okay. As we move into the Pennsylvanian period, so we're getting more and more influxes of those rivers carrying sediment from the east. Sea level is dropping down, and so we start to transition from that ocean environment into more of a swampy forest. We're still very, very warm and tropical. We're located near the equator at this time period, but we're not covered entirely by ocean. You can see on the outline here, there's some oceans to the east, but then the western part of the state is exposed in dry land with that kind of swamp forest. We had a lot of large trees living here called lycopods. They were scaly bark trees, kind of looked like the surface of a pineapple, but they were these huge, massive trees, as well as ferns and other lush vegetation, putting a lot of carbon into the what becomes the rock record, and is the basis of all of our coal deposits in Indiana. So that's where we get the little influxes of black. So that's carbon that has been accumulated by plant material. Okay, here's some of those fossil plants. All right, at the end of the Pennsylvanian time period, as we move into the Permian, all the way up into the Neogene period. So between 299 million years to about 2.5 million years ago, there is nothing. There is no rock record for that time period. That doesn't mean that nothing was happening, but you can see that Indiana was located on dry land. We were exposed at the surface during that time period. And by and large, you accumulate sediment much more easily in marine environments. So we were underwater for a very, very long time, which means we were accumulating sediment that became rock. When we're exposed on dry land, we're exposed to the elements, and so we were largely erosional during that whole time period. So this is a massive erosional unconformity in Indiana, where we have a long, long period where nothing was being deposited, or at least it wasn't being deposited fast enough, or the erosional activity was faster than the deposition. Of course, this includes the Mesozoic time period, the age of the dinosaurs, but we have no record. We have no fossils of dinosaurs in Indiana. It's not to say that dinosaurs wouldn't have been roaming around here, the same as they were in states where we do see fossils of dinosaurs. We just don't have fossil record of them because we didn't have the right environment to preserve their remains as fossils. They would have been eroded and broken apart. Okay, areas where you do see dinosaur fossils are largely in this interior seaway area out west, where they were able to die and get buried quickly in a marine setting. Okay, moving ahead to the Quaternary period, or 2.6 million years ago to the present. This is where we get the Laurentian ice sheet coming down from Canada, giving us the most recent ice age. So again, that had lasted between 2.6 to roughly 12,000 years ago. It covered up to 2/3 of the state of Indiana. Ice reached as far south as the Ohio River in Indiana, and it deposited up to 450 feet of sediment across the state. Okay, the combination of all of these things, the sediments at the surface, the rocks below the surface of the ground, gives us a really diverse amount of geologic features, everything from springs and streams to dimensional rock quarries. We have large valleys that have been carved. This is Shade State Park. We have caves. We have a lot of diversity in our geologic landforms due to our diversity in our geologic history. Okay. With that, I will open it up for questions. And as always, if you think of anything else, you can follow us on social media and ask questions there. At INGeosurvey is our handle on Facebook, Twitter, and Instagram, or you can contact me directly. Okay, I'll come back to that if we have time. Okay. Let me stop sharing here and go back to the screen. I want to open it up for questions, and then if you guys don't have any direct questions right now, I have a couple of slides at the end where we go through time to see how the continents have shifted around and how we know what we know about geologic time. So it's kind of fun, but it's not absolutely necessary. So I keep it as kind of an additional feature in the presentation. Very quick overview. Like I said, several hundreds of millions of years in under an hour. But Indiana, a lot of people think Indiana's flat. It's got to be kind of boring, but it's got, as you can hopefully see now, a long geologic history of complex events. But I think it's also a series of events that's easy enough to understand. When you're looking at the rocks, you can easily tie it to environments of deposition and how those environments have changed. So I think it's a pretty great story. Okay, yes, somebody, thanks to the person who wrote that in the comments there. We will have I'll be giving an earthquake presentation. I think it's in 2 weeks, again on a Thursday at 1 o'clock, and I'll be recording that one again. And I'll cover the seismic hazards that exist in Indiana. So I briefly touched on that today, but if you want to know more about that, come back for the earthquake talk in 2 weeks. Okay, we have a couple of minutes. I'm going to go back to sharing the screen, and we'll go through time. Okay, so if we look at our present arrangement of continents, here's North America, South America. You know, every grade school kid ever has always thought South America and Africa look like puzzle pieces that go together. It's because they did. So we're going to change the orientation here and go back through time to see how these land masses have shifted around. So 20,000 years ago, you can see the Laurentian ice sheet is up there in Canada. 50,000 years ago, the ice sheet extended down. I mean, it covered much of the Great Plains, New England, the Midwest. Okay, and then 35 million years ago, you can see South America and Africa are getting closer together. If I go backwards, take a look at the Saudi Arabia, the Arabian Peninsula over here. Okay, of course, the Arabian Peninsula is a huge source of petroleum resources in the world right now. How do they get all that oil and gas? Well, if we see here at 50 million years, they're exposed at the surface. If we go back to 35 million years, they're underwater. And if you're underwater, you can accumulate organic material that can then transform into oil and gas. So they were underwater, just like Indiana was underwater accumulating oil and gas at a different time period. But this is why they have all of their petroleum reserves there. Okay, getting closer together, land masses moving. Oh, here's India, the continent of India. If we go forward in time again, I just went backwards. You can see India is actually moving north and smashing itself into Asia to form the Himalayan mountains. Okay, but originally it was an island all on its own. And there was actually a marine gastropod limestone at the top of Mount Everest because India used to be underwater and accumulating limestone, and then that limestone has been pushed up into the mountain ridges. Okay. 90 million years, you can see this is when we had dinosaurs. There's that big ocean that separated the North American continent. So that's where we find a lot of the dinosaur fossils. We were exposed at land though, so we weren't accumulating those dinosaur fossils. Okay, 105 million years, 120, look at that. And Africa and South America are reunited. Okay, the continents, if we go back in time a little bit more, are forming together into one of our supercontinents known as Pangea. We've had several supercontinents throughout geologic time. That's just one of the ones that's, I think, the most known. Okay, things are starting to look kind of unrecognizable at this point. Indiana and North America is up here. 240, we're still on dry land, still on dry land. 300 million years. Okay, 340 million years. We're located somewhere around in here. And 340 million years is when Indiana limestone was being deposited, so we were underwater. Okay. Keep going back in time. Things get looking pretty different at this point. You can see the continents have completely changed shapes. 500 million years, 540. At this point, it looks like blue, but it actually would have been frozen over. Okay, here's 600 million years ago. This would have been what's called snowball Earth. It was a large period of glaciation. And when the glaciers melted and it released a lot of oxygen into the oceans, and another reason we had that rapid influx of diversification in the fossil record. Okay, and that's it. We'll go back forward in time now, see how things come together. Lots of collisions and moving around. North America is starting to kind of look like North America again. Okay. All right. How do we know that all of that has happened? A lot of different samples. You got to take geologic samples, and there is a magnetic record of minerals that are magnetic. They're always pointing towards whatever geographic north is at that point, and so we can reconstruct where those rocks are located. We get the age of that rock, and we reconstruct where, you know, they're pointing north. You do that a lot of times, and you can figure out how the continents have moved throughout time. That's the real quick answer for that. Okay, it is 2 o'clock now. I want to be respectful of your schedules, but I will stick around for a few minutes if anybody has questions. Again, I'm going to be posting a recording of this presentation on our Facebook page afterwards, so feel free to check back in with that if you weren't able to catch everything. Thank you so much for joining me this afternoon. I hope it was worth your time and that you felt like you had a good overview of Indiana geology. If you think of any questions, please let me know on our social media pages, and I would be happy to talk about it more with you. All right, I'll stick around for another minute or two, but thank you very much. Have a good afternoon. Thanks, everybody.